Start? Okay, good afternoon, all of you. So, today we will look at connections, basically bolted and welded connections, and then we will go to a tutorial after 1 hour where we will solve one example in whatever we have studied in the last 3 days. Okay, so I'll start with bolted connection. Before that, just an introduction to connections, and then bolted connection. Then what are the types of bolts that are available and how do we install the bolts, then force transfer mechanism, failure of connections in shear, tension and combined shear and tension. Block shear we have already covered in tension members, so I just put it as a list that one more possibility is there. So, generally connections are designed more conservatively than members because they are more complex to analyze. We saw in the limit state chapter that connections, not only connections, even a structure when we are trying to analyze, our analysis gives only an approximate idea of how the structure is going to behave. So, there are issues like stress concentrations and non-uniform state of stress, sometimes buckling. So, all this we are not able to capture, residual stresses. So, all these issues we are not able to capture in our routine design. So, what we are doing is we will try our best to capture as much as possible, but then we will always have some margin of safety, right. So, we do have a margin of safety for working stress design, and also in limit state design we call it as a load factor for margin variation in the load and material factor for variation in material. So, this material factor includes the discrepancy in the analysis and the real behavior. So, that is one of the other major issues. So, in connections what happens is they are so complex that they do produce a lot of stress concentrations, etc., that it becomes very difficult to account for all that. So, what we do is we try to keep the analysis simple and we keep a slightly higher margin of safety. Okay. So, and also in case there is overload, because we do have a load factor, but then load can exceed the working load into load factor, that is called the ultimate load. So, in that case what will happen is the member or connection, something has to fail eventually. So, if the connection fails, then it is like as if multiple members which are connected at that point have failed. Whereas if a member fails, for example in a frame, if only the beam fails in the sense it will, let us say, develop yielding or a plastic hinge or whatever, there could be some redistribution of moment and the structure may survive. So, we try to design it in such a way that it is able to take a higher load even if there is a overload. Okay. So, then connections are again important from the cost point of view because they account for more than half the cost of the construction, that is the structural frame. And then it is very difficult to estimate the cost of connections also, because for example you need to drill so many holes for bolts. Okay, you need to do so many welding. For welding you may have to prepare the edge by grinding the edge and things like that. So, all these issues matter. Okay, so it is very difficult to estimate. It's not just a cost of the material, it's a cost of lot of labor and time costs, time converts into cost. So, if you don't complete your project in time, you end up paying a penalty for that, right. So, all those issues matter. So, we should try, or the designer should try and design connections which are easy to fabricate and even assemble at the site. I would say, like if it is a bolted connection, not only it should be easy to fabricate, but when I take it to the site I should be able to quickly put the bolts. Often they have problem that the bolts may not go in, or due to weld distortions the holes don't match, things like that are quite common. So, we should try to make sure that we are able to do it easily. Okay. So, those are other issues. So, in fact, that is why a best designer is one who has seen how the things are fabricated and constructed or erected at the site. So, just sitting in a design office or in a classroom, you may not be able to understand all the implications of what you are designing. You may draw something, like you may put bolts very close, but then the guy in the field will have difficulty putting a spanner and turning the bolts, okay, tightening the bolts. So, those problems also could come. So, the code just gives you some guideline to help you make sure that you do a better design than what otherwise you would have done. Okay. Then of course connection design has influence over member design. We have seen, for example, let's say in single angle tension members, the length of the connection controls the shear lag, right. Or in single angle compression members, the number of bolts controls the effective slenderness ratio, right? So all these factors become very important. So generally we do a member design and then we do the connection design for that member, and then again we should go back and make sure that whatever we assumed in member design, like suppose I would have assumed 2 bolts, whether I have provided exactly 2 bolts, right? So if I have a, let's say, assumed a net section of some value, so I may have to assume some bolt diameter and deduct the hole for that from the cross section to get a net section. So I might have assumed 2 bolts of diameter, let's say 12 mm, but then eventually when I probably provide, let's say 3 bolts of diameter 12 in the same cross section, my member design may go wrong. So I need to go back and check my member design to ensure that it is still correct. Okay. In the beginning itself, if I assume 3 bolts, then I may be doing a what do you call uneconomical design, right? I'll have to provide a larger member section, cross section to cater for that. So that is also not desirable. Okay. So that is those are the issues in design. Then similar to members, connections are also classified as idealized types, like what we call as, let's say, rigid connections or simple connections. Simple connection is a connection where you transfer only the shear force, right? So you don't transfer any bending moment. You just put it like that, like basically you attach it so that it can transfer only the shear force. And we also neglect, we saw in compression members, we neglect the line of action from the face of the column to the center line. We actually transfer the load at the face of the column, but we assume the column as actually loaded. So we do make some simplifying assumptions so that our design can be completed quickly, but then we should make sure that they are valid to a large extent. Okay. And connections are generally done through, for hot roll steel, they are done through rivets, bolts or welds. Riveted connections have become very almost outdated, because to form the head of the rivet, you actually put a rivet through and then hammer it with a rivet jockey so that you form the head. So the rivet has to be somewhat soft for making the head, and as a consequence the rivets can't take very high loads. Okay, so they shear off at very low loads. That means I need to put large number of rivets. So you might have seen some old railway bridges and all that, steel bridges or plate girders, where you would see a pattern of rivets have been put. But then modern structures don't need to put so many rivets and all, and it's easier to put high strength bolts which take larger force, and you need less number of bolts. So your connections become simpler and economical. Okay. So rivet design is almost not there. So the code doesn't talk much about rivet design anymore, but they can be designed if required, following the same equations which are given for bolts. Okay. And then welding is a very common way of connecting things, because welds, for welds we don't need to put holes, and something we will do in the shop, that is away from the site. Basically what we mean by shop is under controlled conditions. So it's possible that in the site you establish or set up a fabrication shop and do the welding inside that controlled condition, that is in a covered roof, or sometimes we may have to lift the beam, hold it with a crane at the place where I want to do the welding, sit on the beam or somewhere, and then I need to do the welding. So that is called field welding, which is much more difficult, because when you do welding, those particles with hot particles may come out or things like that. So it is dangerous to weld like that. So the weld quality gets affected, and we have seen that to take care of that we use a larger gamma MW, right? So that is, we'll see again. Then the codal provisions. Okay. So the simple way to transmit a force from one plate to another is what is known as a lap joint, where one plate is lapped or overlapped over another plate. And then in this case, let's say these yellow lines actually show the bolts. That is, we have put bolts along the length of the plate. Let's say 2 rows. This could be 2 bolts, or it could be 2 to each. So we are just seeing the sectional elevation. So we see that the force which is applied to a plate, let's say this is the plate, and this could be a gusset plate or another plate. So this could be a plate splice for that matter. So this force actually goes through this and goes, let's say we assume the 2 bolts or 4 bolts share equal load. So half the force, that is, this is T by 2 goes through these 2 set of bolts, and then rest of it goes further, and through the other set of bolts T by 2 will go into the other bolt line, and it will eventually go into the other plate. Okay. But then there is a small problem. There are 2 problems actually. One is this line of reaction or the force in the supporting member and the force in the connected member, they are not collinear, right? So they are actually, there is a small eccentricity between the two, right? So if I apply a force here, I should have actually applied a force along the line of this force, but my force has gone up on the left. So as a consequence, what will happen is this connection will try to bend a little bit because there is a eccentricity. That means basically it's a movement. So my force will bend a little bit, the plates will bend a little bit until the two lines coincide, which is shown in the next figure here. So this is the center line or the line of action of the forces and the reaction. So the plates bend a little bit, but again we can't consider the stresses caused by this bending, etc. And the bending will depend on how thick are your plates, what force you are applying, and so many other parameters. So it's difficult to estimate exactly, but of course we neglect that and we assume that these bolts transmit only the shear force, and that is how the force goes into that, right? So this way of thinking, that is the applied force goes through the first set of bolts, let's say a half of it. In this case there are two bolts, so that is why T by 2 will go and the other T by 2 will go through the second set of bolts. So that is called load path analysis, right? So that is something which you should become familiar with because that tells you exactly what you are trying to do, okay? So if I put two lap splices in series, let's say, but in the reverse direction. So this is my plate which is to be pulled, and this is the reaction plate, but I put what is called as a cover plate like this, and then I transmit this force through these bolts. This may be one row of bolts or two row of bolts, whatever, into the cover plate, and then from the cover plate I transmit it back to the supporting plate, and then it goes through. So I've eliminated apparently the eccentricity, but not really, because if I take a section through this middle part, I still find that this force has to go up and then go through the that plate, and then again it has to come down and become collinear, right? So these are actually two lap connections in series. So here also there will be slight bending. It will bend downwards so that the center line of the upper plate coincides with the center line of the two lower plates. So that is what happens. So this is something which can also happen. To avoid this, the only way we can do is we put what is called as a double cover plate butt connection. Here these loaded plate and the support plate are said to be butting against each other. That is, they are touching each other. So it's said to be butting against each other. And so what is happening is this load now gets transmitted partly half 50% to the top, 50% to the bottom cover plate. So I have what is called as a double cover plate butt joint. And if I take a section now here, I still have, let's say, T by 2 on the top with an eccentricity plus E, and T by 2 in the bottom with an eccentricity minus E, right? So these two movements actually cancel out, and as a consequence this connection will not bend like this, like the lap connection, okay, or like the single shear connection. And another advantage I get is that these bolts now go into what is called as double shear. So if I pull this plate between these two plates, there is a shear plane in the top, there is a shear plane in the bottom. So these are the two shear planes, and as a consequence the bolt strength sort of doubles, okay. So we can always use this type of connection also, okay. So this then the bolts are said to be in double shear, okay, and that is just to transmit a single line load. Like our LCD projectors, etc., are hung from the ceiling, right? So what you find that this is called as a support or a hanger connection. So where something is hung from the ceiling and with bolts put into the ceiling or connected to the beam bottom flange or whatever. So in that case, what happens is, because of this load, the bolts are subjected to tension, right? So the bolts are actually not in shear but in tension. So this is a connection where it's basically supposed to be, it's called a tension connection or a hanger connection, okay. And if you have a connection like this where my load is inclined, like say the wall mounted fan kind of thing, then what happens is this force has two components. The vertical component causes shear in these bolts, and the horizontal component causes tension in these bolts. So these connections are under combined shear and tension, okay. So this is another load case which we need to learn to analyze. So let's see now what are the types of bolts that are available and what are their what is, I should say, properties and all. So first of all, we go to what is called as a International Standard Organization method of grading bolts. Okay, so they grade a bolt. For example, they say a bolt is of grade 4.6. What they mean is that this 4 into 10, that is 40 kgf per mm square, is its ultimate strength, Fu. Or if you want to write, you can write it as 400 MPa basically in our SI units. 4 into 100 will give you 400 MPa as the Fu of the bolt, and the Fy of the bolt, the yield strength, is this second number with a point, that is 0.6 times 400. Okay, so 0.6 times 400 will give me 240 MPa. So that is my yield strength of the bolt. Okay, so Fy is 240 MPa. Okay, so this is how we grade bolts. Currently, the grades which are commonly available are grade 4.6, 8.8, and 10.9. These are available readily in the shop. So if you want to buy bolts of these grades, you can go and buy in the shop. So you don't have much problem. There are other grades which you may want to make specially for some special projects, but generally we try and stick to what's available. Okay, so that is one thing. Then in terms of their behavior, they are classified as black bolts, or basically they are also called, from the behavior point of view, they are called as bearing bolts. Okay, that means they transfer the load by the bolt bearing on the side of the hole. So the minute I put a bolt and I pull, the bolt will bear on the side of the hole and it will transmit load. So they are just put, and then we do what is called as snug tight. That is, we go on rotating the nut till with fingers. Let's say we may use a small spanner, but what we are trying to do is we are not trying to rotate the nut beyond what can normally be done with a very small torque. Okay, so that is called a snug tight position. And beyond that, if I want to rotate it, then I need something called a torque wrench or a spanner with a larger lever arm. So if I put that and rotate, then I'm actually pre-tensioning the bolt. So we don't do that for black bolts. So basically these are grade 4.6, which is, you can see yield strength is 240 MPa and ultimate 400. So it's quite close to the mild steel that we are using, that is 250 MPa and 410 MPa Fu value. Okay, so basically they are mild steel bolts. Advantage is they are cheap. Okay, because they are easy to turn, cut the threads and make the head of the bolt, and because it's a softer material, so I can make the head at a lower cost, and I can cut the threads also at a lower cost. So these bolts become very cheap relatively. So but they are also ductile, because mild steel is ductile. So that's a major advantage. But they are recommended only for static loads. Static in the sense very slowly applied loads. So you may have wind loads or you may have live loads, but these are all considered as equivalent static loads. So we can use them. We should not use them under dynamic or cyclic loads. Like for example, we can't use them in railway bridges, where when a train runs at a high speed, the entire bridge may be shaken, right? So that time they come loose, the nut comes off loose, and sometimes they don't work well. And there's another problem, these bolts, they slip in the hole, so they will not give you a proper rigid connection. They give a connection which keeps slipping back and forth, and that will not only make noise, it will also weaken the bridge or weaken the structure. Okay, so black bolts are only used to be used for static loads. Then there are what are called turned and fitted. So by the way, black bolts are generally fitted in what are called clearance holes. That is, we understand that our members, like let's say an eye section is very long, could be 6 meters long. So holding it and trying to drill a hole in its flange at the exact location is not an easy task. Okay, so what happens is, when I actually connect it and then lifting it with a crane, and I'm trying to connect it to a column or something, so I may have the hole mismatch problem, and if the holes get mismatched, then my bolt will not go through. Okay, so in steel, accuracy of fabrication is very important, because something is 1 mm extra means that member will not go into that gap. Okay, let's say I have a gap and I need to push a plate. So if my plate is little thicker, then it may not go in, and if it is thin, then it will have a play, right? So both ways we have a problem. So we should try and make sure that our fabrication is as accurate as possible, but there are something called tolerances specified. Okay, so the higher the tolerance, the easier to fabricate and erect. Okay, so for this black bolts, what we do is we specify what is called as a clearance hole. That is, the hole will be slightly larger than the shank of the bolt. So even there is a slight mismatch, my bolt may still go in, right? So the hole is generally about 1 or 2 mm larger than the diameter of the bolt. Okay, so they are put in clearance holes. Turned and fitted bolts are put in exact holes, that is not clearance holes but exact close tolerance drilled holes, as the second line tells you. So the tolerance is much lower, and these are used normally in mostly in mechanical engineering, like machines and other things like that. Like in your bicycle, generally you don't have the gap, because if you have this gap in the bolt, then it will start moving and it will rattle and it may not transmit the force easily. So we don't do that. So in most machines or vehicles, we drill a hole of the exact size. We can control better because the parts are smaller in size, so it can be easily held in position, and automatic production lines can be developed because we may be producing the same type of vehicle again and again. So things like that. So they are used mostly in mechanical engineering. And the other type of bolts which have become more popular nowadays are what is called high strength HS friction grip FG bolts, high strength friction grip bolts. So these come in higher grades. So these are grade 8.8 to up to 10.9 are available currently, and they are of course little less ductile, but they have a large strength, and we'll see how they act and how they avoid the slip at the bolted connection. So they are excellent under dynamic and fatigue type of loads. Fatigue loads will come when you design, let's say, gantry girders or crane girders which are lifting the load and moving continuously every day several times. So there could be some issues related to fatigue. So in such cases, we use the HSFG bolts. So as I told you, the force transfer mechanism for bearing bolt, this is what is called as a exploded view. That is, we have removed the two plates and then the bolt is left in the middle to show how this bolt, when it is put and the two plates are clamped together, how it will transmit the force. So if I take, let's say this as my force applied on the loaded plate. So what is happening is this force, this plate will actually bear on the shank. This is called the shank of the bolt. This is called the head of the bolt, and there will be a threaded part, and on this is the nut which will be put on the outside of, that's the bottom of the bottom plate. Okay. So here we are just shown a exploded view, so it has come out, come inside. But then if you pull this, this plate actually bears on this shank of the bolt. These are the orange arrows which are showing the bearing of the bolt on the shank, and as a consequence, the shank in turn bears on the wall of the bolt. So if I am pulling this plate, let's say like this, so my left hand is bearing on the right hand, but right hand is also bearing on the left. So that is, bolt is bearing on the shank also, on the edge of the hole. Okay. So that happens, and then through the shank of the bolt, this force gets transmitted as shear force in every plane, and then at the other end again the similar bearing action takes place, and the force comes out here, and then around the hole it flows in and then goes to the other end of the plane. Okay, so that is how the force transfer occurs in a bearing bolt, and the stresses are called bearing stresses. Then in a high strength friction grip bolt, what we do is we put the bolt and then we pre-tension the bolt, right? That means beyond the snug tight position, we tighten the bolt further. To tighten, let's say I can't tighten the bolt normally. So let's imagine that I pull the shank by some means, like a jack or something. I elongate it by one thread length. So my bolt has become loose, so I can further tighten my net by one pitch. One pitch is the 360-degree of turn of the nut. So that nut moves by one pitch along the threaded part. Okay, so that means I have developed that much pre-tension. So equivalent to the amount of force I would have applied to pull the bolt and make it elongate by one pitch length. Okay, so that is the tension in the bolt which comes. As a consequence of this tension, the bolt grips the two plates tight. Okay, and when the bolt grips the two plates, there will be a enormous friction developed at the interface. Okay, so basically this friction will be the frictional coefficient mu times the tension, that is which is the normal force between the two plates now. Okay, tension in the bolt is same as the normal force between the two plates. So that will be my frictional force, into mu will be the frictional force, and that is why they are called high strength friction grip bolts. So it gives a friction grip. Okay, and even if you put this bolt in a clearance hole or in a slightly larger hole, there will not be any slip. So the bolt is not, shank is not touching the side of the hole. Okay, so it is right in the middle of the hole like this, and it is not touching, but then it will not allow the plates to slip. Okay, So that is how it transfers the load. Okay. So now see, how do we develop that tension? There are many methods. The simplest method, this is I think given in IS 4000. So how to tighten the HSFG bolt to develop the required pretension. So one possibility is something called as a turn of the nut tightening method. So after my bolt or nut becomes snug tight, let's say I take a chalk piece and mark the nut with the plate. So I have a mark which shows that these two are matching, right? Now I am going to further tighten the nut and by 270 degrees, 3/4 of a turn. So I know how much I should rotate, or if I put a spanner, I am going to rotate my spanner by 270 degrees. So that will ensure that I have tightened this nut bolt to its required pretension, right? So we'll see what is the required pretension in the next slide, but that will develop the required pretension. Now, if I don't develop the required pretension, let's say I do only a 180-degree turn, I'll develop a less pretension, and then my calculation will assume that I have some mu into n as the frictional force, but n may be less than what I have assumed. So then the bolt may not be transmitting that type of force, and then when I pull the plates, once I cross the capacity of the bolt to hold the plates together, the plates will slip. Of course, they'll slip into bearing if the holes are not very big, and then bearing also may come into picture. So that becomes an advantage, but otherwise the idea of using a HSFG bolt is to avoid the slip. So that is the one of the requirements. So that is one way. Then we have what are called calibrated torque wrenches. So these wrenches come with a scale attached to the lever and a needle. So when I bend, when I try to apply the torque on the lever, what will happen is this lever will bend a little bit, okay, and the needle will remain straight. So it will show on the scale how much pretension I am giving or how much torque I am applying. And based on the torque, I can always know what is the pretension I have developed. Or there are also mechanical torque wrenches which can be preset for the required torque that it can deliver. Okay, once that torque comes, then the coupling will slip over the nut, so it will not tighten it further. Okay, because if I try to tighten it further, what will happen is I will develop more pretension in the bolt, and there is a risk that my bolt may snap off. Okay, if it snaps off, then again I have to put a new bolt and start the whole process again. I'll lose one bolt. So that is the reason why we should be able to exactly give the required amount of tightening. Okay. Then there are alternate bolt installations like washers with embossing things which can tell you that how much your pretensioned your bolt and all. Direct tension indicator methods are there. So we'll skip that because they're not commonly used right now. The advantage, as I said, of high strength friction grip bolts is I don't need to use the standard clearance hole. I can use what is called as the oversized hole. The minute I can do that, I will be able to drill my hole with less accuracy, right? I mean, I have a larger tolerance. So even if there is a slight hole mismatch, I can still put the bolt, and I'm not relying on bearing of the plate on the bolt. So I'll still be able to transmit my force. So there are also short slotted and long slotted holes which are permitted for only for HSFG bolts. For black bolts, we should go with the standard clearance hole. Okay, so the specifications are given in section 10 of the code. Now let's look at what are the modes in which these bolted connections can fail. So we start with first the shearing of the bolt. You can see as we increase the tension, these bolts have sheared off and practically they have the connection has failed. Okay. So basically the shearing strength will be a function of the shear stress into the area which is getting sheared. Now often we have bolts which are partially threaded or which are fully threaded. Both types of bolts are available. That is the entire shank length. I may only thread one part of the length of the shank, let's say half the length, or the entire length of the shank can be threaded. So depending on which cross section comes, that will be govern the shearing strength of the bolt, right? So generally we should assume that if the bolt is in single shear, we should assume that the shearing plane comes in the threaded section, right? So that is the root area of the threads, and of course there are specifications which tell you what is the depth to which you should cut the threads and all, but then you can go with a simple assumption that the what do you call the shearing area AS, or the net area we can call it, that is at the root of the threads, as 0.8 times the gross area. So you should remember this is a ratio among the area, not the diameters. Okay. So this is 0.8 times A. and that into the whatever is the shearing stress. Shearing stress will be typically Fy by root 3 gamma, sorry, Fu by root 3 gamma M1, okay, or MB. In this case, we are talking about bolts. So we will change gamma to gamma MB, and that will be our shear Fs. So that way we can calculate. Then bearing on bolts, you can see here this plate is being pulled, and these two plates are pulled on the right side. So there is a small cut here which has happened. That is, the plate has actually bitten into the bolt, right? Because the bolt may be soft and the plate may be of higher strength steel or relatively harder material. Then we say that the plate bears on the bolt. Okay, if it's the other way, the bolt crushes the plate, like the plate is soft and the bolt presses it like this. So then we say that the bolt bears on the plate. So whichever is the softer material, that Fu we should take actually, right? So that would be the divided by gamma m naught or gamma mb will be the value for this, into the area on which the bearing actually occurs is the projected area, which is the diameter into thickness. Okay. So diameter here we can't see, it is in the depth of the slide, and thickness we are able to see here like this. So that would be the projected area on which bearing occurs. So that is how we calculate the bearing stress. And the bearing on the plate is also similar. Basically, we take the Fu of the plate divided by gamma m1 and then into dt will give me the bearing on the plate. Now, if the plate end distance is less, then what happens is again it facilitates bearing. Okay, so the code says there should be a minimum end distance such that this value will come greater than this. But if you are provided less than that, then you may have to reduce the bearing strength alternatively. Okay. So those are that's basically the conceptual calculation, and then we go to the actual equations which are given in the code. The code IS 800 section 10.3 talks about bearing type bolts, and in that 10.3.2 talks about the shear capacity of the bolt. So VSB, the B for bearing shear bolt, S for shear, and V is the shear capacity is given by Fu by root 3 gamma mb. So as I told, Fu, the minute you see, you put gamma mb or gamma m1 below that, which is 1.25, and since it is shear, the if Fu by gamma m1 is the shearing strength, is the ultimate strength and tension, then shear strength will be Fu by gamma m root 3. Okay, so that root 3 comes into, basically it should have been the number of shear planes into the corresponding areas which are getting sheared. So let's go back to, let's say, this double shear case and see there are two shear planes, one is here, one is here. So this may be the head of my bolt, this may be the nut at the other end, and let's say the bolt is threaded to 50% length. So that means this shear plane will be the shank area. So I'll say number of shear plane shank areas which are sheared is 1, NS is 1, and AS is the diameter of the shank into pi square by pi by 4. So pi by 4 ds square will be the AS. So that is one area which is getting sheared. The other area is getting sheared at the net or the root area, which is, as I showed, the 0.8 times the gross shank area. So that, and how many planes are getting sheared? Only one plane is getting sheared. So in this case, this will be 1, that will be 1, and the corresponding areas. So NN is 1, NS is 1, the corresponding areas you have to take to get the total shearing stress. Okay. So it's, if it is in single shear, it is recommended that you take NS as 0, NN as 1, and ANB as the root area at the threads, right, or the net area. Basically, N stands for net. So that is the area you have to take. If it is multiple shear, that is there are more than 2 cover plates or whatever, then you have to find out what would be the correct numbers to take and things like that. Then another assumption is that we go back one slide, and let's say I apply this load and there are 2 rows of bolts. So we assume that these two will transmit equal load, right? If this is T, let's say if there are 4 bolts like this and I'm pulling like this, so this two will, each bolt will transmit 1/4 of the total shear, right? So that is a normal assumption. But what happens is if the joints are very long, then the extreme bolts tend to have a larger shear, okay, compared to the middle bolts. So the variation in the shear stress is not uniform among the bolts. Now instead of trying to find out what is the variation and trying to consider that into account, so it's again a form of, I would say, stress concentration. Stresses concentrate more on the extreme bolts. So we don't want to get into details of how much they concentrate and things like that. So what we will do is we will use a slight reduction factor for the bolt strength, and those are given here. So reduction factor in shear for long joint. So basically it says if the length of the joint is more than 200 times the diameter of the bolt or whatever, Lj is greater than 200, then you have to use this formula. If Lj is less than 200, this probably will be or basically the beta Lj has to be between 0.75 and 1. So this problem will come when you have more than 2 bolts along the direction of load. Okay, so if you have more than 2, then you work out what is your Lj. Lj may be n times the number pitches that you have between the bolts. So that would be my possibly my Lj, length of the joint. In the first bolt and the last bolt, that distance is called Lj, and that divided by 200d. If I subtract from 1.75, I may still be greater than 1, in which case I should take beta Lj as 1. Okay, or if I go below 1, if it becomes 0.9, I can take, but I need not go below 0.75. So that is how the code reads. So beta Lj is between 0.75 and 1. Okay. Then reduction factor for shear in large grip lengths. So when your bolt is having a large grip length, again I'll go back and explain what is grip length. Grip length is the distance between the bottom of the head of the nut, head of the bolt, to the bottom of the nut, right? Bottom in the sense the inside part of the nut. This is the outside part. So this is my grip length, and the grip length becomes very large, the bolts tend to bend a little bit. Again, I don't want to complicate the analysis considering bending. So I apply a reduction factor for shear for large grip lengths. So if my Lg is greater than, let's say, 5 times d, then beta Lj will be less than 1. Okay, so 5 times d plus 3 times d, 8d divided by something larger than that would give me beta Lj less than 1. Okay, that's how we have to understand. Then reduction factor for packing plates. So sometimes what we do is we need some tolerance in the thickness direction also. So we may put let's say larger clearance. That means instead of this plate is going to be, let's say, 6 mm, but I give a clearance of 7 or 8 mm, and then after assembling, if there is a gap, then I'll fill it up with a 2 mm thick washer or something. It's very easy to drill a hole in a 2 mm thick plate. I'll drill and push it in, right? So or I may use pieces of plates like washers under each bolt. So it may not be a single plate over the entire connection, but one piece here, one piece here, like that. These are called packing plates. So they also contribute to bending of the bolt. So that's a reduction factor for packing plates. So these are the reduction factors which have to be multiplied to VSB to get the correct value of the VSB. We proceed to the bearing capacity of the bolt. As I said, bearing capacity is nothing but the bearing stress into area. So in this case, we are saying that 2.5 Fu by gamma MB will be the bearing stress. Okay. So if something is to do a tension test and it breaks at Fu, but if you are pressing it, something hard on it, then depending on the hardness, you may get as high as 2.5 Fu as the bearing stress divided by gamma MB into dt is my bearing strength for one bolt. So we calculate the shear strength, we calculate the bearing strength. The smaller of these two is called the bolt value, and that can be used in design to calculate the number of bolts required. So the total force F divided by the bolt value will give me the number of bolts required, and then I have to arrange those bolts in some pattern so that my joint becomes complete. Okay, so that is the equation. Tension capacity is same as what we did in tension members for a threaded rod. Like what we did was, we said due to threading, the gross area will reduce to root area of the thread. So again, you can assume the root area at the threads as 0.8 times the gross area, and into A, that is An itself is 0.8 Ag into FUB by gamma MB, and again 0.9 because tension rupture is sudden. Okay, so that 0.9 comes. So this part for the time being you can ignore, this normally wouldn't govern. So anyway, you have to check for the yielding of net section, right? So when you do that, you will automatically be doing this. So you will be checking for the yielding of the bolt also. Okay, and bolt subjected to combined shear and tension. So we saw in one of the connections in the beginning, this connection, we had shear due to downward force and tension due to the horizontal force. So when that happens, we calculate the shear capacity as the shear and the bearing capacity smaller of the two VSD. That's called the design shear capacity of the bolt. And we calculate the tension capacity, design tension capacity with this equation. We put these two in the denominator, and the actual shear and tension which are coming on the bolt, they are in the numerator, V and TE. So this square plus this square will be less than 1. So we basically plot, let's say, V by VSD on the y-axis, T by TND on the x-axis, and if you plot this is the equation x square plus y square equal to 1. So it's an equation of a circle. As long as you are inside the circle, it is safe. If you touch the circle, you are going to fail. I mean, the bolt is going to fail. Okay, so that's how we check the bolt. Let's go to now shear connections with high strength friction grip bolts. So as I said, the bolt is developing a normal force. Let's assume it as F naught. So basically mu times F naught should have been my shear strength, right? So that is what we find here. The slip resistance is basically mu F, the friction coefficient, into F naught. Okay, there are two more numbers coming. Again, F naught is doubtful, so we put a gamma MF below that to take care of that. And then there are two more numbers. One is NE is the number of shearing planes. So in double shear, NE will become 2. Basically at two surfaces I'll get friction. That is, I'm pulling one plate between two other plates. So I have friction here, I have friction here, right? So that is NE will become 2. And KH is a reduction factor for larger holes. So it is 1 for clearance holes, but more than 1 for other holes. So it's very simple to understand. First you write mu F naught by gamma MF, and then multiply with single shear, double shear, triple shear, whatever, and then put the clearance factor KH, and then you get the shear strength of the bolt. Okay. Now what is that F naught? F naught is the proof load. As we know, it is made of high strength steel, so there is no yield strength specific for it. So we are trying to estimate from FU. Now we are trying to go back to the proof load Fy, let's say. So proof load are the load at which the bolt has been pre-tension. We actually try to pre-tension is less than the proof load, because the minute I reach the proof load, the bolt will start yielding, and as it yields, I will not be able to pre-tension. I'll actually be losing my pre-tension, right? So that is why we try to stress it for a slightly less value. It also will bear, and the bearing will give 2.2 dt FUP of the plate by gamma MF. So we are assuming that FU of the bolt is larger than FU of the plate, so it is going to, bolt is going to bear on the plate. So FUP is for plate and divided by gamma MF, that is the friction coefficient. So this is basically the same formula, and the coefficient of friction is to be obtained from a table. We'll see the table in a minute. These are the KH values, 1 for clearance holes, 0.8 for oversized and short slotted holes. That is, if the hole length is along the length, it is short, and if it is long, then it is to be taken as 0.7. Okay, and again there are two conditions given. One is if I want the slip resistance at service load. So in, let's say, what I should call, let's say in a column splice, I don't want any slip to occur at service load, because then my column will tilt. Or in a beam splice also, I don't want normally slip to occur, because then beam will deflect or it will move a little bit. So it will cause discomfort to the occupants. So then I will try to avoid slip at service load. But then if it's a connection where I don't mind it slipping at service load, but I don't want it to slip even at ultimate load, then I'll have to use a larger gamma MF. Okay, so that there are two criteria. Then F naught is that force that we are pre-tensioning, is called the minimum bolt tension at installation, the way we are pre-tensioning the bolt at the site. Okay, so that is the 0.8 times the area into small f naught, where f naught is taken as 0.7 times FUB. Okay, so irrespective of the grade of the bolt, you can take it as 0.7 times FUB. So for example, we go back to the bolt grades, we have two possibilities. Here it says it is 0.6 times FU. Anyway, this we are not using for HSFG. Here it says 0.8 times FU is the yield strength, but we are taking it as 0.7 in the HSFG bolt design. So here it is 0.9 times the ultimate strength, but again we are taking as 0.7 because of we don't want the bolt to elongate. Okay, so that is why the code says you take it as 0.7. So that is 0.7 times the ultimate strength of the bolt. which is the first number into 100 in MPa. So that gives you, like if it is a 10.9 grade bolt, 10 into 100 is 1000. That is my FUB, the bolt. 0.7 of that will be 700 MPa, and that is my F naught. And F naught into 0.8 of area of the shank will give me the F capital F naught. That is which I am going to use here in the calculation. So that is about this. Now coming to the coefficient of friction, obviously if I want friction to develop, I will not put grease or oil or even paint, because paint is a soft material, it's an organic thing. So it will enable the plates to slip. Okay. So plates which are going to be connected by friction grip bolts, that part alone we will never paint. We will put the bolt and then we will put spray paint on top of the joint, but we will never paint the surfaces which are trying to develop the friction grip. Okay. So as the steel is produced in a steel mill and it comes out, because it's hot rolled, so it cools in the air, so it develops a scaly formation. You would have seen some design on it, a fresh steel, you will see like the skin of a fish. So it's called a clean mill scale. Okay. So that gives you a friction coefficient of about 0.33. But if it slightly gets rusted, little bit rusted, but or if it is sand blasted, that is if you clean it, clean the rust or some grease or whatever with sand blasting, then the sand particles will make the surface little more rough than what you get in a clean mill scale. Okay. So then your friction goes up. Or if you paint or do galvanizing, zinc is again a very soft material, so then you are actually reducing the friction coefficient. So if for example I need let's say n number of bolts at the clean mill scale, it is 0.3 let's say, so I'll need 3 times, that is if I need let's say 3 bolts on a clean mill scale, if I'm going to galvanize and then connect with friction grip bolts, I'll need 3 times that number of bolts because my coefficient has become 1/3. Okay, so I would try and avoid this. I'll try to get as much high coefficient as possible. Okay, so if I get 0.5, then at least I'll get less than that number of bolts required for clean mill scale. So that is how it does have an implication on how you construct. Okay, so you may assume something in design, but same thing has to go through drawing to the site, so that a similar procedure is followed at the site. So they'll write all this as notes in the drawings. Coming to the bearing capacity, we have seen this 2.2 Fig. Tension capacity, same formula which we have seen. Shear and tension for friction grip bolt also quite similar to the bearing bolts. Okay, so there's no reduction. All the reduction factors will apply here also. Okay, so that is one thing. This is that hanger connection which we saw in the beginning. This is the hanger connection. If this plate, this is called the end plate, or the if the plate is very thin, then we get an extra force on the bolt. So it tells you how to calculate the prying force. I think we may skip this for want of time. So the code gives you an equation, not like this, but it's a slightly different equation which gives you how to calculate the prying force. All you have to remember is, if you are using a hanger connection or an end plate connection, use a slightly thicker end plate, so the prying force will not come and you don't have to do the calculations. So okay, that is one simple way of avoiding the problem. These are spacings and other things which are given in the code, so that you are able to tighten, put a spanner and rotate it in the site and things like that. So, and also there is no local buckling between the bolts or compression buckling between the bolts, things like that. So then we come to, let's say, 2 connections which are important. So these are typically, let's say, beam to column connection. This is called a simple connection, where I transmit only the shear force. That is, I connect only the web of the beam. You know that an I section, the shear is mostly carried by the web and the bending is carried by tension and compression in the flanges. So this is a movement connection where tension and compression will develop, and those flanges have to be also connected. Okay. So in any complicated connection like this, what we do is we assume that the connectors, that is the angles, or this what is called as a web cleat or a web angle, these are not going to deform much, so we neglect their deformations, and that is we are assuming that they are very rigid, and then we do a simple analysis to understand, that is, if this angle is not going to bend or anything, it is going to be like a plane section in beam and it remains plane, so my stress distribution will be linear, right? So our strain distribution is linear, so that is an assumption which enables me to calculate the force in the bolts. Okay, so those are written here. Let's go and see how do we actually do it for real connections. So in these are called, for example, in trusses, if the member axis coincide, then it's a concentric connection, and if they don't coincide, sorry, this is also a concentric connection, they are coinciding, but in reality we can't put a single bolt like this. So what we do is we use a gusset plate and we open up the connection, so we are able to actually fabricate and connect it more easily, but we try to ensure that the center lines coincide, okay, in the detailing. If it is not, then we get extra forces in the bolts. That is what is shown here. So my load is, instead of coming concentric to this group of bolts, it's coming eccentric. So this is called a movement connection. In this case, we say that the movement is in the plane of the gusset plate or in the plane of the bolts, okay, and here it is out of plane. So in this case, the due to the movement, there will be extra shears coming in the bolts, whereas in this case, due to this load, there will be extra tension coming in these bolts, okay. So this load will of course cause some shear in the bolts, but apart from that, the bending moment will try to put more tension in the upper bolts, okay. So these bolts are under tension plus shear, so that has to be now accounted for. That will depend on the extra tension, will depend on this eccentricity, okay, from the face of the column or the shear plane of the bolts to the line, loaded line of the load, actually where the load is acting. So let's look at one such connection which is subjected to, let's say if we, in this case that P is shown as inclined, but let's assume that it is a vertical load Py along the y direction, and it is at a distance x dash from the CG of the bolt group. There are 6 bolts which are put in a group. So this is basically a bracket connection, and what is happening is now we are trying to analyze and see. So what we are saying is that the shear coming in these bolts due to the vertical component Py will be distributed equally to the n number of bolts. So each bolt will have a vertical shear upward reaction of Ry I, which is Py by n. Okay, n will be 6 in this case. So that is how we are calculating the direct shear, and the shear coming due to the movement caused by this Py. So what is the movement? Py into x dash is my bending rotation, that is the torque that is coming. So what now we are going to assume now is the resistance caused by the bolt, the extra shear that is coming due to the movement, is proportional to the distance of the bolt from the CG of the bolt group, okay, Ri. So what we are saying is Rmi for the movement, the resistance to the movement is proportional. This is a proportionality constant K into Ri, okay. So that means each bolt will resist a moment Mi, which is given by K times Ri, which is the force into the lever arm Ri, okay, K Ri square, okay. From this I back calculate K as Mi by Ri square and substitute here. So I get resistance at Mi is, instead of this K, I am now going to put as Mi by sigma Ri square, Mi by sigma, the total M by sigma Ri square into Ri. So this Ri directly comes here. So that is the Ri here, okay. So I find that my force in bolt can be obtained, and these are again vectors. So they have to be combined by vector addition. So either I know the inclination of Ri, so I know the inclination of Rmi, so I can resolve it as a horizontal shear and a vertical shear. The vertical component will directly combine with Ryi, which is what is done here, this one, and the horizontal component is adding up to, in this case there is no Rmi in the x direction, that is there is no Rxi if the load is vertical. So this will not be there, but this will come, okay. So this square plus that square, the two vector addition will give me the resultant. Square root of that gives me the vector addition Ri. So that is my total force, and this should be less than the bolt value in shear, okay. So depending on whatever bolt it is, if it's a bearing bolt, the bearing bolt capacity, or if it's a friction grip bolt, the friction capacity of the bolt. So that is one simple analysis. Then if it is out of plane movement, eccentric connection, so I applied a load or a bending moment M such that the bolts are going in tension. So what I do is I assume, in this case what we say is, if there is a no soft spot, in the sense the plates, the column flange and the end plate are bending slightly to accommodate this movement. So then I assume the neutral axis approximately at d by 6 or d by 7 from the bottom edge or this edge of the beam, and that is my neutral axis. So I am saying that the tension in the bolt is proportional to its distance from the neutral axis. So Ti is K times Li, where K is my proportionality constant, and that into the lever arm. Lever arm is to be taken with the center line of action of the compressive force C, okay, which I may assume as acting. In this case, it's a triangular compression, so I can assume at, let's say, d by 1/3 of d by 6, that is d by whatever. And then if I have a stiffener here in the column, then I would say that this will act exactly at this point along this line of the bottom flange plate. Then that will be my Li. Okay. So I have shown two cases, possible cases for capital Li, and so M is sigma of Ti Li, where Ti is K small Li. So I summation of Li will come, and then Ti back calculate. So here again you get K from this equation, M as Ki is equal to M by sigma Li. So that I substitute here, and multiplied by small Li will give me the tension in the top bolt. Okay. So this is the tension in the top bolt, and if there is a shear V, so V by number of bolts, N will be the shear in that bolt, and these two I have to combine with the circular interaction equation and show that under combined shear and tension the bolt is safe. Okay. So this is how we analyze a typical connection. Now let's proceed to welded connections. So there are many advantages of welding. The basic advantage is we don't have to drill a hole, so we are not cutting or reducing the member cross section. So that is a major advantage. Direct transfer of stresses. So we are not adding any extra plates, so no weight, no cost, etc., etc. So there is also a lot of cost saving and neater appearance, and it gives a very rigid connection. So that these are the basic advantages. Welding is done by several processes. For slow or small works at the street corner fabricator, they use gas welding. For most other work, structural work, we use what is called as electric arc welding. So which uses electrical energy. So what we do is we use, I think there is no figure here. What we do is we have something called an electrode, which we bring towards the surfaces to be welded, because there will be an electric arc due to the potential difference. We connect this to the cathode and this as the anode. So let's say we bring that. So there will be a spark generated which will melt the metal. Not only this metal, it will melt the electrode also a little bit, and then the electrode metal will get deposited to fill the gap, and the whole thing becomes a single weld pool, that is like a molten metal, and when it cools it solidifies and it gives you a continuous medium like a metallurgical bond. But there are some problems in that. One problem we already know is that because we are heating to a very high temperature, and steel is a good conductor of heat. So if I heat locally here, the heat will get conducted away from there. So it cools very fast. Okay. So as a consequence, due to heating of a local place, you get high residual stresses. So welding produces huge residual stresses. It also changes the metallurgy of the material. The weld metal as well as the area around welding is called the heat affected zone. So there the metallurgy changes and the material becomes little bit brittle. So that is something which sometimes leads to failure, especially under fatigue type of loads. So there are some disadvantages of welding, but then the major advantage is it enables us to connect huge sections without any drilling of holes and all that. Sometimes we may have to prepare the edges. We'll see when we have to do that, but otherwise it's okay. It's been, once you do a good welding, probably you will be able to overcome many of these issues. Okay, so that is it's developed as a science of its own, and people study only welding and things like that. They do research on welding. So there are many welding procedures, and the important issue is how much heat or voltage that you are applying, and how much you are able to melt it, to what temperature you are able to heat that locally, the welding position, and then how the welding is going to cool. So if I probably weld a vertical plate, let's say to a horizontal plate, I weld along this. When this weld cools, it will pull this plate a little this side because it's cooling. So I'm not going to get a 90-degree angle which I want. It may bend. So either I hold this plate like that until the weld cools, that which may require elaborate arrangements, or I weld a plate little on the other side inclined. So when it cools, it becomes 90 degrees. So there are many techniques which welders develop by experience, and they can do a very good welding. So that is shrinkage and what is called as weld distortion. So there are again lap splices, T-joints, corner joints, there are many types of welds, but mainly the two types of welds are important. There are four types of welds. They are the butt weld, or like when you connect the two plates butting against each other and weld it there, that's called a butt or a groove weld, because to make a butt weld we need to make a groove. So it's also called a groove weld, or we do what is called as a fillet weld. So we just weld outside and that is a fillet weld. So sometimes when if we don't have place, we go for plug and slot welds. Okay, I think there may be pictures here. So this shows you how we cut a V-shaped groove in these two plates. There are two plates which are actually butting, but we grind it and make a V-shaped groove, because depending on the thickness, my weld electrode will not, or the welding may not penetrate the thickness of the plates to be welded. So if the plates are anything more than 3 mm, then welding cannot melt a metal which is thicker than 3 mm. Okay. So what we do is, this is called the depth of penetration of the weld. So to increase this depth of penetration, that means I can weld only this much and this part remains unwelded, which will cause cracks, okay, or it will not be efficient transmission of load. So I cut a V-shaped or whatever shaped groove, and then I start welding from this. So that first line of weld is called root run. So I deposit 3 mm of metal, and then I do filling runs. Each run will deposit 3 more mm of metal. So if it is a 10 mm thick plate, I'll have to do at least 3 runs, and then probably a capping run, because I would have still reached only 9 mm. So I put 3 more mm or 2 more mm, and I'll cross that 10 mm, right? So I'll have a metal which is little more than the parent metal, and then if I don't want that projection, I can always do grinding and come back to a smoother surface, right? So that can be done. So both multiple runs are done, and then between runs also, because the weld metal cools in the air, it produces some kind of a slag formation which has to be chipped off, cleaned up, and then again the next run has to be done, right? So there are many procedures for welding. So all that has to be properly followed. So that gives you a groove weld. If I don't want to do the edge preparation, I will keep the plates lapping. I'll weld here, I'll weld here. That gives me what is called as a fillet welds. So that also helps me transmit the force. If this overlap is not adequate due to some reason, let's say that means the length of the weld is not adequate fitting here, then I'll cut a circular hole, I'll fill it with weld. It's called a plug weld, or I'll cut a elongated hole and weld around that hole, so that I'll get extra weld length. So that is called a slot weld. Okay. So these are 4 types of welds which are done. So basically this are similar to be designed as fillet welds, and this is the butt weld. Okay. And butt weld, we actually don't need to do any design. We just need to take care that the weld metal is stronger than the parent metal. So, and we have done the full depth weld, so that, and the full length, full width of the plate is welded, so that when I pull, the weld will be stronger than the parent metal, and then the parent metal is the one which will yield first. Okay. So if it yields, it will give a warning, and then we can take steps to either remove the load or avoid the structure. Okay. So that can be done. So those are some of the advantages, disadvantages. As I said, disadvantages: high residual stress for butt weld, edge preparation, and proper aligning. You can't probably align the two plates exactly. If you weld a little inclined, then you are in problem, right? Or sometimes you may align it and weld, but then due to weld cooling, weld distortion, the plates may go up. So you need to clamp them properly until the weld cools. So those are the extra precautions to be taken. Then it gives good resistance to impact and cyclic stresses, etc. Fillet welds have their own advantages. They have ease of fabrication and adaptability. I don't have to cut the plates exactly touching, butting each other. I can just overlap. That means I have tolerance. Little more, little less doesn't have a, it's not a problem. Okay. So it requires less precision in the fabrication, no edge preparation. What happens is, in the fillet weld, any plane can fail. Whether let's say I pull this plate with reference to the lower plate, then either this plane can fail, that means the plate will move along with the weld, or the plate will leave the weld and it may fail in the vertical phase, or it may fail along any inclined phase. So generally the failure occurs along the inclined phase, because if this is S and this is also S, so this becomes S by root 2. Okay, so that it always tries to fail in the minimum. This is called a reinforcement, which is little bit more. We don't know how much it will be. There's no guarantee that it will be there. So we take the failure plane for a fillet weld as S by root 2. Okay, where S is the size of the weld, and with reference to that and the stress, that is shear stress, that is developed in the failure plane, we have to calculate how much is the length of the weld required. Okay, so the symbols are given in some other codes. These are used in the drawings. So basically, let's see. Yeah. So for fillet weld, my shear stress, that is stress due to individual forces, P divided by 0.7 S is my stress that is developed, and sorry, 0.7 S is the uh, size of the weld per millimeter length, into LW, length of the weld. This is the area of the weld, into what is my FU by root 3 or whatever, FU by root 3 gamma MW, right? Gamma MW will be 1.25 it is sharp weld, 1.25 it is field weld. So this stress is to be multiplied with the area, which is 0.7 S LW, and that gives me the length of, I mean, the force that the weld can take. So this should be larger than what I am trying to transmit. Okay, that is how we design a fillet weld to transmit direct shear. Similar to bolted connections, we can also have what is called as eccentric connections. Like if you imagine I weld along these three sides only, and I apply a load in the bracket, I have a CG of the weld group will come here, somewhere here. So this is like a channel projecting out of the plane of the screen, so which is under P into E, that is the torque. Okay, so torsional stresses will develop, which are basically nothing but shear stresses, and the stresses will be in proportion to the distance of the point from the CG of the weld group, weld line or weld group as we call it. Okay, so we first need to work out the CG of this. For this, you can either assume that L into 0.7 as the area and take moment of that area and locate the CG, or alternatively 0.7 is common throughout, so you can just take L into its moment, right? So then finally you can adjust with the 0.7 S that you have. Okay, so length of this into its movement about, let's say, the bottom line I take, then the vertical length into its movement about the bottom line will, and divided by, so total, this will have 0 movement, divided by the total area, that is the total length in this case. If I do, then I'll know what is the CG at which the CG is located, the CG of the group is located, and with reference to that I can calculate R, and then based on the polar moment of inertia, that is T, torsion T by IP into R max will give me the maximum shear stress that is developed, and that should be less than the stress in the weld that the weld can take. So that way we can design this connection. Okay, so that completes a quick run through of the connection design, and we'll now open for questions. So if you have any questions on connections, you can ask, and I'll try to answer them. Okay, one question has come. Which connection is economical and why? Each connection has its own, I would say, advantages, disadvantages. Like if you want to fabricate something in the shop, then probably welded connection may be advantageous. There are shops where automatic welding can be done. So you just pass, let's say you want to make an I section with 3 plates, you just pass it through the rolling line, and then automatically robotic type of welding can be done. So then it becomes cheaper, the weld becomes cheaper, and good quality also comes through. If you have to sit somewhere and weld in the field in the hot sun, then it is again uneconomical. So it may be easier to take the beam there, put the bolt quickly, and come out of that place. So each connection, I would say, has its own advantages and disadvantages.
Yeah, good afternoon, sir.
Good afternoon.
Yeah, my question is that in the case of a plate girder, the weld that we design for connection of the flange and the web, there's an expression given in the book that they should be designed for a certain force. And normally they say that this force is because this is the shear because of bending of plate girder, shear between flange and the web. But when you look into the expression, there's a shear force in that expression, V, that comes at the end, maximum shear force.
Okay.
At one point we say that this is because of bending. The shear is because of bending, but in the expression we consider that vertical shear force. So I mean, how do we explain that? I don't remember that expression exactly right now, but vertical shear force comes into that.
Okay,
Force
okay.
between.
No, I don't think vertical shear comes directly into it. Basically, suppose we don't weld a flange and the web. Let's imagine. Okay. So what will happen is when I apply the load, there will be something called longitudinal slip. Okay. What will be that longitudinal slip? For example, if I'm going up to MP, right? That means between the flange is transmitting a compression C, which is area of flange into Fy by gamma m naught whatever. Okay. So that is the CF we will call force in the flange. That force has to be part of the bending if it is to be connected, right? It is actually coming all the way from the top down. Similarly, there's a tension in the bottom flange is coming down. They are neutralized at neutralizing each other at the neutral axis level, right? So that is the force that's called longitudinal shear. It will depend on the bending moment that we are applying on the section.
Yes.
Okay, that is
But in that expression, that vertical shear force is also considered. I mean, if you look into the books, that is given
yeah,
there.
vertical shear also may come because, as I said, if you apply shear on the web, there's something called complementary shear which develops. Yesterday we saw, right? A complementary shear pattern which is developing. So that may also cause some force. So maybe that is also coming into that. You can send an email. I'll look into that and answer you more correctly. Okay.
Okay, okay. Thank you. Yes, please come. One more question.
Yeah, sure.
You can just ask.
So in the case of riveting, we use gross diameter. Rather, in the case of bolting, we use nominal diameter. So what are the causes of it?
Uh, what do you mean nominal diameter?
So in the case of riveting, when we
Whatever is the
calculate,
shank diameter, let's say 12 bolt, means the bolt shank will have 12 diameter. Okay, so we have to use that only. But then the chance is that we are cutting threads for putting the nut, right? So the threads may come in the shear plane. So that is why we may use the area at the root of the threads in the case of a bolt. Okay. Oh, you're talking, okay, the whole diameter will be larger for a bolt compared to the shank diameter. So 12 bolt will fit in a 13 hole. Okay, but when you take a rivet, what you are going to do is you are going to put a rivet and hammer it, and when you hammer it, what it will due to Poisson's effect or plastification, it will expand and fill the hole. Okay, so if it is a 13 hole, it will fill the 13 hole completely. So you take the same as the hole diameter. Maybe that's what you are asking.
Yes, sir.
That is what happens.
One more question, sir.
Yeah.
Good afternoon, sir.
Good afternoon.
Sir, my question is which type of connection we must prefer provided the eccentricity and force is same.
Okay.
Whether in group moment bolts should be preferred or out of the moment group bolts should be preferred.
Again, it's a question of I would say the convenience in fabrication and erection. So how are you going to attach the bracket or whatever? So out of plane, you can understand. Let's say I want to connect a beam to a column, okay, and I want to do what is called as the out of plane is also called end plate connection. Correct. So then my two end plates should be exactly positioned. That means I have to cut the beam first of all in the correct size, and then after that I'm going to weld the two end plates, and the outer edges of the two end plates should be exactly matching as the clear distance between the column faces. Then only I'll be able to lift my beam and quickly bolt, right? If it is little less, then there'll be a clearance, so I'll have a problem with the gap. Correct. So if it is more, my beam may not go between the two columns, right? So in such cases, you may have problems. So we may have to think how are we going to tolerate those errors in fabrication at the site, right? So that's why some tolerance is required.
Sir,
So
there is no
different people use different connection. Like the pre-engineered building industry uses end plate connection because they are able to accurately calculate and do the end plate design. Okay, they are able to fabricate to required accuracy, whereas some other industries they prefer other types of connections.
Sir, there is no role of the kind of force that is I mean to say in kind of in group moment group it is shear force, and in out it is tension and shear force group. Both are acting. So whether it is
Correct.
not the reason.
No, that is not the reason, because we are designing for both. So I mean, either way, we are calculating the effects of that, and then we are taking it in the design. So both connections will perform to our expectation. Okay, so that is not an issue, but the issue is which one would be convenient for me to make and erect, right? With the given accuracy that I can work with. So that is what is generally governs.
Thank you, sir.
So let's quickly have a few tutorials. First one is a worked example on design strength of a tension member with 3 bolts. So determine the capacity of the plate 100 by 10. So this, let's say this distance, width of the plate is 100, thickness is 10 mm, and there are 3 holes of diameter 13 mm. Basically the bolts may be 12 mm dia bolts, and assume the yield strength of the ultimate strength of the steel to be 250 MPa and 410 MPa. Normally I don't give this in exams. I ask the students to find. I just say it's my steel. So you can assume this most of the time. So and this is the pitch. This is called the end distance. So that need not be any restriction on the end distance. Actually, the pitch plus end distance will also govern what is called as the block shear failure. So if I don't provide adequate end distance and pitch, I may have block shear failure in this member. So I have to check that. Let's assume some values for all this. The gauge distance G, you can see how it is between the 3 horizontal lines. The distance is 20-20. Okay. So hopefully that adds up. Let's say whatever. That's why I have not shown the edge distance here. By the way, this is, if I am pulling this plate, then this perpendicular distance is called the edge distance, and this parallel distance is called the end distance. Okay, so here we are not concerned with edge distance right now. So design strength as governed by yielding of cross section, clause 6.2, Ag Fy by gamma m naught, total area into Fy by gamma m naught. This 1000 is for converting Newton to kilonewton. So I get 227.3 kilonewton. Design strength as governed by rupture of net section. If I take a zigzag, first let's take section 11, which is going through 1 bolt hole. So that gives me 870 mm square. Then 212 is possible. This is 212. This is a zigzag section. So that is a possible cross section. Now you have to realize that many people check section 22 also, but section 22, if you are checking, you have to check for only 2/3 of the total tension, because 1/3 has already gone through this bolt into the gusset plate. So by the time you come to section 22, you will be actually checking only for 2/3 of the total tension, right? So generally it may not govern unless I put 1 bolt here and 3 holes here, let's say. So then section 22 may still govern, but in this case section 212 is what will govern. Okay, so this is my 1510. So obviously the smaller of these two is 870. So I take 870 and calculate as 256, which is still larger than 227. So basically, even though we have put holes, the holes are not so big as to govern net section to govern. Okay, so the cross section yielding is what is governing, which is good. It is supposed to be a good design. That is, efficiency is 100%. Okay, so and then the block shear failure for again 3 bolts. Code is silent on how to take block shear. So I tell people to take a equivalent rectangle. So in the top line you have 1 bolt hole. In the vertical line also you have 1 bolt hole, and this bottom line also you have 1 bolt hole. So based on the corresponding net areas and the gross areas, we get TDB1 as 237.2, which is again luckily more than this one, and TDB2 is coming much higher. Okay, so basically the cross section yielding is governing, and that is 227.3 kilonewton. Okay, so this is the first example. Let's go to design of a I section for axial loading of 900 kilonewton. So the column is 4 meter long and is fixed at the base and pinned at the top. So based on that, you have to take the effective length. Column is restrained at mid height from deflecting about its weak or bending about the buckling about the weak axis. So weak axis is the YY axis. So if there is, generally what we do is we orient the column in such a way that if this is a room, it goes around, and the beam connects to the column in such a way that the strong axis bending is what will govern. Okay, so that is one possibility. And then in the minor axis buckling, we can provide a strut at the mid height. So this strut probably will go in a wall, and the bracing also will form part of the wall. So the effective length about the weak axis will not be 4 meter, it will be half of that, because we have provided a connection mid height. At mid height we are restraining. So now it has to bend in a double half sine wave, sorry, 2 half sine waves, that is a full sine wave. So we have to understand that effective lengths will differ in ZZ for buckling about ZZ and buckling about YY. The R values, radius of gyration also will be different for ZZ and YY. We get that from the steel tables. RZZ is 123.7, RYY is much smaller. That's why we have to restrain, otherwise this may govern the load that we can put on the column. And these are of course section properties of ISMB 300. A required, if I assume 150 MPa, A required is around 6000. So I choose something around that. Not necessary that it should be more than, because I have yet to verify what is the thing. So I just try, let's say ISMB 300 with some area close to what is required. Then I check for buckling about first YY. So both ends are hinged. So the effective length is coming to half. So slenderness ratio corresponding to that, L by RYY, KL by RY 70.42, and this K is taken from table 11. And then from, we have to be careful which table we use. So table 8B is for column buckling class B, that is a rolled I section buckling about the YY axis. Okay, so that's a minor axis. So then for that we can directly use the corresponding xi value from the table. It's better to always calculate xi and then calculate FCD, although tables for FCD are also given, because this tells you what is the efficiency you are achieving, right? So it is about 73.9, 74% efficient design, and into Fy by gamma m0 gives me 161 MPa into effective area 5626 gives me 907. It just passed 900 kilonewton. Okay, so it is safe. Then let's go and see what happens about ZZ axis. End condition, one end fixed, other one hinged. So K from the table is 0.8, and 0.8 into 4000 is 3.2 meters long. Slenderness ratio corresponding is 25.8. Lambda we can calculate. Then based on depth to width ratio we check. Thickness of flange TF is less than 40. So for that, these two conditions from table 10, we take curve A, buckling of a hot rolled I section about ZZ axis, curve A, corresponding imperfection factor. So instead of going from the table, now I am calculating phi, lambda and all that, and then FCD comes out as 213. I can also use the tables, and capacity comes out as 1199. So it's much higher, but I can't reduce because YY is governing. So I will not be able to do anything about this. So we accept the design. Okay. So it's just safe and also very economical, I would say. We proceed to single angle strut. So we take design a single angle of 2 meters long to carry a factored load of 180 kilonewton and connected by one of its legs such in this way. Connection A is single bolt of diameter 16 mm grade 4.6, and connection B is 3 bolts of diameter 10 mm grade 4.6. Just to understand what happens, what is the effect of connection on the strength. So maximum load height, assume some value FCD, let's say 100 or 105 or whatever, because angles are generally very slender. Even at 2 meters you will get a large lambda value. So try some angle and check. So basically you can choose any angle. Single bolt of 16 mm diameter grade 4.6. So effective slenderness ratio given by this class, where I need to take K1, K2, K3. This is okay. Yield stress can be 240 because it's less than some thickness. So in the code, I think here there's a mistake. This is epsilon in the code, but later on an addendum has been issued by Bureau of Indian Standards which tells you that this is Young's modulus E. So correct your code accordingly. Lambda VV is L by RVV. This 19.4 what we got. I mean we can get 19.4 for this from the steel tables, and so L by RVV is 2000 by 19.4. If I take this as 20, it is around let's say 1, right? 2000 by 20, so it's about 100, right? Yeah. So whereas lambda VV with this comes to 1.16, correct, or a little more, and then lambda phi comes out like this. Now we have to calculate K1, K2, K3 from table 12 of the code. We find that for number of bolt 1, that is single bolt, so it is hinged in the plane of the gusset, and gusset we are assuming as thicker than the angle, so it is fixed in the out of plane of the gusset. So for that K1, K2, K3s have been taken, substituted here, and lambda E is obtained as 1.2. Always compare this effective with your lambda VV. Lambda VV is 1.16 and it is slightly more because, so it's okay. So it's actually helping us because gusset was fixed. Okay. So imperfection factor alpha is 0.49. You have to use the C curve for an angle, whatever may be the buckling axis, corresponding phi, and FCD comes out as 96 into AE gives me 185 kilonewtons, which is just greater than 180, which has to be taken. So it is safe. So that is how we are getting a safe design. 3 bolts when I go, same angle, K1, K2, K3 will change as per the end conditions, and then I find lambda E comes much less than lambda VV. Okay, so because of 3 bolts, there is some end fixity which avoids or helps in avoiding the flexural torsional buckling, and as a consequence, my FCD goes up. I think previous FCD was only 96 or 97. Now it has become 124. So with the same area, it is coming much more safer than before. Okay, so this is how this also is passing through. Next is a beam bending example. We have taken a design bending strength and shear strength of a laterally unsupported beam. The beam section is given to you, ISMB 300 of span 5 meter and supported laterally only at the ends, and factored UDL that we want to back calculate what is the maximum uniformly distributed load that I can apply on this beam. Okay, this beam is laterally unsupported. So I write down the beam properties first, then I do section classification. For column also we should have done, but ISMB sections are generally, they will pass the semi-compact limit, so there's not much to worry. For beam, it's only a question of which most ISMBs will pass semi-compact limits. Only ISWB may come out as semi-compact, so you may have to use MY rather than MP. But here, just for completion of the sake, we are doing the what do you call, the section classification, and we find flange is plastic, web is plastic. So the section is classified as the worst of the two, which is again plastic. I mean, basically both are plastic, so this is plastic. Now, elastic lateral buckling movement, MCR. So there are two options. One is to use this big formula, the original formula for any beam. Other option is the simplified formula for an I section. So that also you can try, where you need H by TF and IYY. So that can also be, could have been used, but here we are using the big formula. So we need to calculate the warping constant and the torsional constant, IT and IW. IT is given in under the formula itself as summation of VT cube for all the component plates. So an I section is made of 2 flange plates and a web plate. So 2 flange plates of width 140 and thickness 12.4 cube by 3, and sorry, this should have been plus, this should be plus 300 minus the flange depth, okay, flange thickness at the depth of my web into thickness of the web cube by 3 gives me the IT torsional constant. Warping constant is given in annex E as this. Basically it says that for I sections you can take it as 0.5. I think you can directly, yeah, 0.5 for I section. So that gives you, and H will be D minus T. So you can use this also if you want. The shear modulus is given in right in the beginning, section 1 of the code itself. All the properties, Young's modulus, Poisson's ratio, shear modulus are given. So G also you know. So substituting IY from the steel table, KL is now 5 meters. that is 5000 mm. So MCR comes out as roughly 93 kilonewton meter. This is a theoretical load for an ideal beam. So now for a real beam, we have to convert this MCR into a corresponding lambda value with this formula Fy by Fy into Zp is my MP by MCR, square root of that gives me lambda as 1.32 and it is greater than 0.4, and for this I need to go back and calculate with the help of that lambda LT. I need to calculate chi LT and FBD. Okay, so chi LT into Fy by gamma m naught gives me FBD. So that is coming out as 104. So okay, we don't have FCR here directly. So what we will do is we'll multiply MD is ZP into FBD. So if you multiply, you get 68 kNm. So this is compare with this with the theoretical value 92 or 93 kNm. Okay, so the critical buckling load for an ideal beam was 93. So it would have gone flat and then curved the theoretical curve. The practical value is like the strength curve. So it comes much less than that value, right, 68. So this is due to imperfection and residual stresses and all that. So this design bending it can support is 68 kilonewton meters. Now corresponding UDL it can take is of course 21.8 kNm factored UDL, that is WL square by 8 is compared with that. Now what is the shear it can take? If W is the UDL, it will be WL by 2, and the shear capacity because it's a hot roll section, there is no question of web buckling here, so it will only yield. So yield capacity Vp is AV into Fy by root 3. I should have also put this is called the nominal capacity in limit state design. When you divide by gamma, you get the design capacity. Okay, design strength of the web is 295 kilonewtons, and corresponding UDL it can support for this, that is WL by 2 to be less than 295. You get W to be should be less than 118. Okay, so sorry, it should have been yeah, kilonewton per meter length of the beam, which is way high compared to this. So it's not going to govern, right? So that's not a problem. So I can easily put 21.8. So without having any shear failure of the web. So that is the final answer. You should also check with deflections. So in this case, elastic deflection we worked out for a simply supported beam with UDL W, and we find it as 10.31. If you go to the code table 6, it says that for simply supported beams, the deflection under live load should be less than L by 300. Okay, so span was 5 meters, so 5 meters by 300. I don't know how much it will come. If it was 600, 6000 by 300 would have come 20 mm. So this may be little less than 20 mm, but my deflection is much less than 20 or whatever 18 mm or whatever. So that is also okay. So basically this beam is governed by the bending capacity due to lateral buckling. Okay, so that is what is governing. Okay, so that is the beam design. We have two more worked example. One is on bolted out of plane, in plane movement connection, a bracket connection. Bracket is welded to ISHB 400 column. So this is my column flange which is coming on the face, and then the bracket is bolted with 6 bolts of HSFG. It has to carry a 100 kilonewton load at 200 plus another I think 70, so 270 mm from the CG of the bolt group. So that is my total, the total width is 140 for that ISHB 400. So bolt force Px is 0, Py is 100, total eccentricity is 325, 200 plus 125, sorry this was 250. The gauge distance has been taken as 140, and M is obviously this is the in plane movement that is coming. Try the arrangement shown as shown. 60-60 is my whatever you call pitch distance, and gauge distance is 140. So I have to calculate the distance of the farthest bolt from the CG of the bolt group, and also all this. So actually you can do it in a tabular form. Maybe if you want, you can group the bolts as first group, second group, and things like that. In fact, the first group all RIs which are equal will come. So there are actually 4 bolts which are at a distance, let's say 60. This is this distance is 4 bolts which are actually the shear will come like this due to movement in the horizontal direction. So they are at 60 mm from the bolt. I think there should have been, so we are adding xi square plus yi square. That's why we are not trying directly getting Ri. We are getting Ri square as sigma xi square plus yi square. So xi for these 4 bolts is 60, yi is 70. Okay, so that is 6 bolts at 70, and so we get sigma Ri square, and then the Ri due to the movement and due to the shear. So each bolt now carries 100/6 as vertical shear, and vertical shear due to the bending moment is this much, horizontal shear due to the bending moment is this much. So the total net shear is roughly around 81.8 kilonewtons. Bolt capacity, it's an HSFG bolt of diameter 20. So mu f we have assumed 0.48, but typically I would recommend you assume 0.33 if you don't know what is going to be the. So here we are assuming sandblasted surface, which may not be the case. So let's assume 0.33 for normal design. KH is 1 clearance hole. F naught for the grade of bolt is taken as something, and it is worked out as 85. And ISHB 400, the bolt capacity DT thickness is 8 mm. So diameter is 20. So it is coming out as 104, and the bolt value is 85. Obviously, slip will govern for an HSFG bolt. So it is just coming safe compared to the load coming on the bolt. Finally, we have a last welded connection. We are going to weld an angle at the heel and the toe. So, and applying a load of 80 kilonewton with an eccentricity of 40 mm. So if this angle is like this, and if I am applying a rotation like, so 80 into 40 will be the bending moment applied, and this will be resisted by shear, which will come as a sort of a tension here and bearing here. Okay, and that plus 80 kilonewton shear force also has to pass through these 2 weld lines. So for the rolled IS section, this is ISHB 300 whatever. Flange width is 250. So that means that length of the top and bottom weld is 250 mm. So shear force for 1 mm weld length we first work out. That is 80,000 into 2 into 250. That is 160 newtons. Bending moment about the face of the column is 80. That is 80 kilonewton into. So these are the actual loads coming on the welds. Force in the weld per 1 mm length due to bending moment due to this 32 kN into 105 is the I think 105 is taken as the capacity of the weld divided by 250 into 100, so giving me 128. Resultant shear force due to shear and bending is coming as 205, and this should not exceed the design strength of the weld. Length of the weld is let's say let's take the size of the weld as S into 0.7 will be the throat thickness into 125 is the length of the weld. So that should be greater than, sorry, 125 is the capacity of the weld per millimeter length. So that should be greater than this 205. So the weld has to have a size of at least 2.34 mm. Okay. So we will provide a 3 mm weld size. So it doesn't matter if it was, if T was coming out as let's say 3.5 or 4 or whatever, I'll provide the next higher size of weld. Okay. As I said, typically weld sizes of 3, 4, 5 mm can always be provided. After that we go to 6, then maybe 9 or multiples of 3 mm is what we commonly do. Okay. So that can also be done. So this is the last problem. Now again we'll open it for, I'll keep it in this slideshow mode. We'll open for questions. Interaction with PECUT SK Verma. Good afternoon.
First of all, is there any guidance regarding the block shear patterns to be identified?
The code gives you only that rectangular pattern. So the block shear rectangle, the perimeter should encompass all the bolts that are there in the connection. Okay. So that is how. So today I showed you in the worked example that triangular pattern with 3 bolts. So since we are having only a rectangular guidance in the code, so I said you can use a equivalent rectangle which passes through the 3 bolts.
Sir, even if you identify the rectangle, there can be many shapes of the rectangle. One can be from along the edges, another can be along the bolt line. So
No, net section we have already considered in the design of tension member. Lines like 1 vertical line 1 through the first bolt, that we have already considered as a net section in the design of the member, right? That is second equation in the code. First is yielding of cross section, second is the rupture of net section. So the vertical and the zigzag section we have considered in the rupture of the net section. The third one which you are considering in block shear is like it comes off as a block, so it's a rectangular pattern, so that top and bottom lines are in shear and the vertical line is in tension rupture. So that is the only pattern that needs to be considered.
sir, while calculating the tension strength of the angle member, there was a factor beta accounting for the shear length factor.
Correct. Yeah.
Means the exact formula I don't remember, but otherwise there were two components. One was for the connected leg, one was for the outstanding leg. For the outstanding leg, there was a factor including beta, and that beta accounts for the shear leg factor.
Correct.
Now the query is, if beta turns out to be more than 1, there can be situations as given in the code, beta can be more than 1.
Can be more than 1. Yeah.
If beta is more than 1, that means the area, instead of because of the shear lag, rather than having any adverse effect, it is having more than the normal area effect. Is it acceptable?
No. Beta you can multiply with. You are actually multiplying beta into Fy by gamma m naught. So what we can say is the stress is maybe more, average stress in the outstanding leg is more than the yield stress. Okay. So that into you can multiply with either area or you can multiply with what you call the stress, right? So we should think of it as a stress being more than the yield stress by the factor beta. Average stress, it can actually go up to ultimate. If there was 0 shear lag, then beta would become like almost 1.4, that's the higher limit allowed. So 1.4 is generally the factor between Fu and Fy. So 1.4 Fy would take you close to Fu. That means the entire section is fully effective under and is rupturing under as a net section. Okay. So, but that may not be the case due to length of the connection and other factors, shear lag and all that. The stress will be between Fy and Fu. So beta can be more than 1. So it's not an issue.
So there is no problem with that.
Yeah.
Okay, sir. Then in the laterally supported beams, while one of the assumptions was the movements at the two ends are equal.
Correct.
Movements means we will be treating a beam as a laterally supported if the movements at the two ends are equal. This was one of the conditions, no?
No. The MCR value that we calculate is by that formula is for a beam which is laterally unsupported and subjected to uniform bending moment. That is the two ends there are movements M. Okay. So that movement is called the lateral buckling moment MCR, critical moment MCR. So now for other loading conditions there is a table in the code which converts, let's say, a non-uniform bending moment into an equivalent uniform bending moment. So there is a factor called xi which converts, let's say you have a triangular bending moment for a point load in a beam. So that you can convert into an equivalent uniform bending moment, and then we compare with the MCR of a beam under uniform bending moment. So that's how we look at it. Okay.
That means it is accounting for both the uniform as well as the gradient.
No, basically that once I convert, let's say my maximum bending moment is M max. So I will calculate xi as, let's say, 0.8 of M max or something. So I will say that instead of a triangular bending moment with M max in the middle and 0 at the end, I am going to assume a equivalent uniform moment of 0.8 M max, where 0.8 will be my xi factor, and for that these two beams will buckle at the same critical moment. So that's what we are looking at.
Go ahead. Normally, for normally the situation is that when there is a dynamic loading, we should
Okay.
go for the tactile type of the behavior.
Yeah.
Normally in the structures, that is desirable. Okay,
Yeah.
when it is subjected to dynamic loading, we should go for the tactile type of the detailing.
Correct.
Whereas in the bolted connections, we are concluding it otherwise. Means that we are saying that HSFG bolts, which are not so ductile, having a strength of something like say 8.8. So
Correct.
it is not a ductile material, but we
Yeah.
are recommending it for the dynamic load. Any specific reason?
Yeah, actually, I'll answer it this way. So, what happens is, let's imagine we have a chain, okay, normal chain with made up of links. So, let's imagine one of the links is brittle, okay. But if this brittle link has higher strength than the ductile links, just imagine if I go on pulling the chain, what will happen? First, the ductile links will start yielding. First, one link will yield, the next link will yield. So, all the ductile links will yield. They may yield and then they may strain harden, and if at all they reach that strength of the brittle link, then only the brittle link will fail. So, we can look at this bolt as a link which is brittle but stronger than the other parts of the structure. Okay. So, there are many methods of designing structures so that the brittle links will not fail, but the ductile links will fail. That is the key to the something called capacity design, and that is what we do in most detailing.
Bearing stresses, we are
Correct.
taking it as 2.5 FU.
Correct.
Bearing stresses while calculating
yeah.
the bearing strength.
Yeah.
I mean, is there any background behind this thing? How we are
Yeah,
arriving
people
at
have like we test soils for bearing. What we do, we put some let's say small plate or something, or cone penetration test. We put a cone, press it down and see how much load it takes to go in, right? So similarly, people have put small areas, I mean on loaded areas on plates, pressed it and checked at what load. We are talking about not a plate which is unsupported, it is kept on something strong. Okay, let's say on the anvil of the blacksmith, and we keep a plate and we try to, let's say you keep a coin, okay, and then you press the coin with some other screwdriver or something. You press it and see, and then you know what is the area of that screwdriver tip that you have, what is the load at which it could dent that coin, right? So if you see that, you will find that there is a factor of about 2.5 for the biting into the material. Okay, so that is that FU, 2.5 FU. Prying force, yeah, I did not cover, but anyway, tell me. You want me to go to that slide?
I said there are some forces, prying for PRYING,
Understand.
prying forces. I mean, can you explain slightly the mechanism of these prying forces and how they are to be encountered?
Okay, I'll go to that slide and explain to you. So basically, what happens is prying force is nothing but a something similar to, you must have seen carpenters pulling nails out of wood with a what is called as a prying hammer. Okay, so the hammer has like two tongues. You put each one around the nail, so the nail is caught between these two, and then instead of pulling the hammer out, you press the handle down, right? What you do actually is you pry the nail open. Okay, that means if I have a plate like this, I'm showing in the slide, and if I'm pulling this up the lever with 2T, then I would have expected a force of TT in each bolt. Okay, so but what is happening is the tip of this plate touches at the other support plate here, and it bears on that, and when I'm trying to lift this pull this plate here out here at this time, because the plate has become little bent, okay, that is because of the less thickness of the plate. So this tip is touching here and pressing down with a force Q. So what happens is my bolt has to not only resist T from here, but a Q also. So force in the bolt becomes T plus Q, and the formula tells you how to calculate this Q. Okay, and the formula in the code tells you how to calculate this Q. But if you do the calculation and if you use a thicker and thicker plate, eventually you will find that for a fairly thick plate, Q becomes 0. So that means if the plate is very thick, it's not going to deform like this, then there will be no prying action. But if the plate is not thick enough, there may be prying action, and if you don't consider in that as equilibrium force, then your bolt may shear off at T or little more than T, because T plus Q is acting on it. So that is the answer. Okay. Yeah, that's for welding. So as I said, if something yields at let's say Fy or Fu, then it will shear off at Fu by root 3. Okay. So when you are combining normal stress with a shear stress, this becomes a yield criteria. A Q, that is Q square plus F square plus 3Q square, that becomes the total stress.
That's what I am trying to ask you. What is the background of this formula?
Background is basically you can draw the Morse circle and then combine the two stresses. It will be actually background is something called the yield criteria in the materials. So there are two criteria, Tresca and von Mises criteria. So both criteria will give almost a factor of root 3. So we have used for bolt and all that the shear force, no, Fy, for example, Fu by root 3 in shear, and then we are trying to combine with tension, right, under combined shear and tension. So automatically the denominator part, we are using that bolt strength VSF or the bolt value we are taking for shear with a factor of root 3. So that is quite similar to that. You can just work it out and you will find that it will come quite similar to this expression. So this one I have written only for weld stresses.
While combining the load, where we have defined gamma F, that is table 4 of IS 800.
Fine, go ahead. Yeah.
Certain combinations. For instance, the combination is dead load plus wind load oblique earthquake.
Okay.
Now, there are two 1 by 5 table more easier to I mean, my query will be more easier to explain. There are two factors, 1.5 reacted 0.9. Now the query is which one is to be used at this instance?
Okay. So there are two lines. Yesterday also this question was asked, day before yesterday when I talked about limit state design. So what we are saying is that if we are taking a larger live load, then we can take 0.6 of the wind or earthquake load, or if we are taking a smaller live load, then we take 1.5 times wind or earthquake load. So both have to be checked. Okay. Both load.
Both the values have to be.
Yeah, both. So you analyze for this combination, whatever bending moment you get, that is one. You analyze for next one, whatever bending, whichever is the larger of the two, you have to design for the larger bending moment.
Thank you.
Yeah, thank you. Plate girder, I said we can't go in. VNPB 2.5 kb DTFU, I think probably I have answered that indirectly. What is kb? Kb, as I said, is called the what do you call the whole coefficient, you can call it. So that is for this thing. Then what is meant by OMF? I think he's going into section 12 of the code where we talk of ordinary movement frames, which are non-ductile frames, which take lateral load by movements, developing movements at the connections. Okay, so those are OMFs. Then steel code book, of course, I think we should not expect students to remember the formulae, so they should be allowed to use IS 800 without writing anything on that. So they can be allowed to use the code book. Then how to provide column splice. Column splice is given, two examples are given in the last appendix F of the code. So if you can open up your code, you will find that there are two possible splices given. One is you put double cover plates on the flanges and also on the webs. Okay, so that is one possible way of doing a column splice. Other possible way is you put an end plate on the bottom column, end plate on the top column, and then bolt this through like a end plate connection. So these are the two possible way of connecting columns. And okay, one more from Jagbir. For a plate girder, when the classification of flange and web is different, and the worst one is for web, shall we consider web classification for calculating bending strength of the member? Yeah, actually, okay, for plate girder you are asking. For plate girders, generally we assume or accept, the code accepts that the web will classify as slender. That is, it may be susceptible for buckling. Webs will get susceptible for buckling after the d by tw crosses 67 epsilon, whereas web will get classed as slender for neutral axis in the middle if you cross 125 or 126 epsilon. Okay. So if the web d by t is greater than 125 or even whatever, let's say if it's slender, then what we do is we ignore the contribution of the web to the moment capacity. So if I am doing elastic analysis, I'll assume the only two, what is called as a two plate section, the two flange section. I'll ignore the contribution of the web to the moment capacity. I can calculate the moment of inertia of the two plate section as area of the plate into the distance square from the neutral axis square, right, AH square. So that becomes the effective, into 2 will be the effective moment of inertia of my cross section, and that into Fy by gamma m naught will give me My, which will almost be same as MP in both. I mean, so we can calculate the moment capacity that way, which is actually ignoring the classification or the web. So we can still use the section for resisting MP calculated by ignoring the web. Okay. Plate girders are generally provided when the load is very heavy or when deflections govern the design. So plate girders are also used in some buildings in some rare cases, or as transfer girders. Okay. Okay, then there are no more questions. We are saying goodbye. Bye.